The multi-telluride is interesting, but what's interesting about multi-telluride is it can run 3 different structural phases.
Oh, yeah, right.
So it can actually be in the semiconductor polymer, it can be in the semi-metallic polymer, and so forth. So if you can find a way to some people have shown that you can use some techniques to crystal flake, that's one type, but you do something with this half and it changes it, and you can get this clean interface between the 2 different, like a semiconductor and maybe metal. That can be really interesting, have this clean mating of the and then you can make devices out of it. That would be really cool.
But is it topological?
Yeah, totally.
Yeah, so Liang proposed this in his original paper. The problem is that the electric fields, the displacement fields necessary to achieve that are a bit high. A little bit too high. But it doesn't mean that similar somehow the gap is just let's say factor 2 species. Then maybe that would it may just make some there's already some tunability. I think that we're starting to see if we get the devices he said it after some aliens we're going to accept it. It's not a one of these. Yeah, okay. Everything is essentially you won't tell. Right, so that might give you a set point that's very close to the transition. Maybe that gets close to the transition. And then a little bit of not the acceptance. Then to be accepted. That's what it was. How you do it to be accepted? I think here goes it's not to be punished. It's accepted. Cool. Yeah, that's what I'm saying. Not exactly. I try to type something. I mean, the thing is, like, a lot of things happen on large densities. And like, oh, you think, wow, that's very cool. To do the same thing in a low density scale is harder. So one of the cool things that I have a chance tomorrow. I have a very small. So he said, he wrote me, we don't get a lot. You can just still change your execution by 70. It's not yeah. So we have we heard some otherwise would just be that's all accessible. No, so it's if it proximity has to equal then yeah. I'll give some. I'll flash some prospects for people. I just have I'm still sometimes using it, so I will call. I'm not doing it today. I'm not doing it this time.
The one about the next one is
Yeah, I know. Yeah, I sometimes do it. Okay.
Let's see, we're waiting for the host here for a couple of minutes. I just want to say that we're back to good behavior here, and we have a sign-up list for the ES294 people that need to sign up before they leave the room. And those, when we didn't ask you, you all get credit for the time we didn't ask you, so don't worry about it. Thanks. You're the host.
You want a mic? Can you speak up? Yeah, you introduce yourself.
Okay, hello everyone. So it's a pleasure to have today Valla fatemi with us to give the sequence, frontiers for the devices seminar. Valla is a student in my group. He's been doing excellent work on topological insulators in 2 dimensions, and he's going to tell us all about it.
Thank you, Pablo. Hello? Is the mic doing anything? Okay. Thank you everyone for coming. I'm excited to present all of our work here on tungsten ditelluride, where we have a number of different interesting electronic states that we'll be observing. However, I like to recognize that science is a human endeavor, so I want to recognize all the people involved in the effort. So Pablo, as my advisor, who's just introduced me, Sanfeng, who joined us only a short year ago, and in partnership with whom we've managed to get a lot of great results on the monolayer results, which will be towards the end of the talk, at the second half of the talk. And of course, all of the members of our group and the theory collaborators we've had, as well as the materials growers, in particular Bob Kava and his student, who have given us the excellent tungsten ditelluride crystals that we've been using. So because I understand that this isn't a course of some kind, I'm going to give a background on 2D materials and topological systems in electronic matter, and then move on to our work in tungsten ditelluride. So 2D materials, to begin, is this whole class of materials that have sort of taken over condensed matter physics, or at least some quadrant of condensed matter physics, beginning with graphene, the discovery of which was awarded the Nobel Prize in 2010, and many other materials to follow, including nitride and molybdenum disulfide and many others. So this table is where much of the early work was done and continuing work, starting with graphene and boron nitride and the semiconducting chalcogenides like molybdenum disulfide. We can also add more rows since this time, so there are halides now that can be an entirely independent row on this table. But here on these chalcogenides, we see a few rows in the background which are meant to identify varying levels of chemical instability. So in green and in red are supposed to progressively put ultra-thin tungsten ditelluride maybe in the red column, for example. But this will be an important point in my talk a bit later. One of the conceptually amazing aspects of 2D materials, not that it necessarily makes research easy, is the so-called Scotch tape technique that many of us are probably familiar with, where we simply have a rock and a piece of tape, and you put the tape on the rock, and you get these thin regions, which we can then place onto a silicon chip. And once we peel the tape off, you see this fuzziness. When you look a little bit closer, you see actually these are little 2D crystallites of, say, in this case, monolayer graphene. And as a bit of nomenclature, for those of you not familiar with the field, what does a monolayer mean? Well, in the case of graphene, it's pretty simple. You have a single atomic sheet of carbon, which is actually less than the unit cell. So we see that this has nothing to do necessarily with the unit cell of the three-dimensional parent compound. And this gets a little bit more, slightly more complicated in other systems that are not graphene or boron nitride based, where, say, in tungsten ditelluride, which this represents, we have a 3-atom thick monolayer. So you have a tungsten atom sheet at the center and tellurium atoms on either side. So this single covalently bonded sheet is what we call the so-called monolayer that is the thinnest limit that we can get to with the Scotch tape technique. And this van der Waals bond between the sheets that's so weak that we can pull it apart with Scotch tape is just as good for putting things back together in a way that you can stack sheets onto each other reliably, but it doesn't matter what the different materials are. You get sort of a mix and match Lego block concept for putting together all sorts of different kinds of materials. And so here, instead of emphasizing the particular chemical compounds, actually what's interesting is the different kinds of electronic states in these materials that can be put in touch with each other. So we have the classic materials, and now we have metals, semi-metals, superconductors, ferromagnets, charge density area materials, and then as well topological insulators, which is the second conceptual portion of this talk. So let's give start with a cartoony introduction to what a topological insulator is. So imagine that we have let's say two-dimensional insulators, or any kind of insulator, and you slap them onto each other. And you put your DMM on that. What would you get? And generally, the resistance should be quite large. Okay, it doesn't do anything more interesting than these two insulators themselves. And so I'll suggestively put these numbers that indicate something very deep and fundamental about the way that the electrons are held in place inside of these insulators. Then when you let's imagine that we can have something that's not 0 but say a 1, something very different about the way that about this insulating state. We say that okay, these things are actually topologically distinct, and I'll clarify this word a bit later. But here in this sort of schematic band structure, we have a conduction and a valence band, and the color is meant to signify something about, say, the orbital structure that is changed across this interface. And in this case, where we have, say, a two-dimensional insulator with this number that we'll call a Chern number, and you have a difference of 1 across the boundary, if you do this ultra-simple two-terminal measurement, you have this arrow that represents a chiral mode that will give you a resistance, a two-terminal resistance of h over e squared.
across this system. Now, one thing that's important about these topological systems is that in principle, it doesn't matter how exactly the band gaps are aligned or how disordered this interface there, this state will always exist. And so in that sense, we call it topologically protected. Finally, just as you need a reference for your voltage to define what voltage you're applying to anything, you also need a reference for your topological quantum numbers. So it turns out that vacuum, fortunately, is an insulator and it's topologically trivial, so that serves as our reference quantum number. And so for any given material, you can look at its band structure and isolation and understand what is the topology of that system. And then you, let's say with vacuum, you will always have some kind of. Now, a little bit at what this number means, we often see this analogy with geometric systems. So we have, say, this sphere. This is a Bodum cup, so this is a vacuum gap here, sort of like a squash sphere. We have the torus and the coffee mug with torus and this little mechanical object with 2 holes there. So it turns out that with all 2D manifolds, closed 2D manifolds, you can have a generic classification where that can be computed as follows, where you define the local Gaussian curvature, integrate it over the entire manifold, and with a small manipulation, you get an integer that is known as the genus, that literally counts the number of these holes. All closed 2D manifolds can be classified this way, and this number cannot be changed without tearing, so-called, in some sense, this manifold. That's a very drastic action from a mathematical perspective. And so for 2D electronic systems, you can literally just copy-paste some words into this procedure, and you get exactly the same thing. So what this is really saying is that symmetry-protected topological systems and quantum Hall systems is literally a classical topology of a quantum geometry. And the quantum geometry is the Berry curvature here, in the case of a 2D electronic system. So we have this classification of 2D electronic systems, where you define the local Berry curvature for each band that's occupied. You integrate it over the entire Brillouin zone, and the result will be a number, in this case, called the Chern number. All 2D electronic systems can be classified this way, and the Chern number cannot be changed, and this is the important point, without closing the band gap. Okay, that could cause a topological phase transition. This was first understood in the context of the quantum Hall effect. So imagining you have a simple 2D electron gas, you apply a perpendicular magnetic field, and due to Lorentz motion and quantum mechanics, you'll get Landau levels. Here you have these bands that are caused by the magnetic field, and in this case, we have energy and density of states, and our chemical potentials here. So we have these 2 occupied bands. We can do exactly this procedure, or something very close to this procedure, and find that each of these Landau levels contributes a Chern number of 1. So if we have 2 bands occupied, you get a Chern number of 2. Here I'm drawing only a single chiral edge mode, but the point is that in the quantum Hall systems, it was recognized that each Landau level contributes this topological invariant known as the Chern number, and this is a key component, is one of the key components of the Nobel last year on topological systems. And much more recently, in the new millennium, it was discovered there's something more you can do with so-called symmetry-protected topological states. So here is a 2-dimensional time reversal invariant topological insulator. The notion is that that looks like it might be just some typical mode that has both forward and backward moving carriers, except that when you look a little bit closer, you see that, say, the red mode has spin pointing in a particular direction, and the purple mode has spin pointing in exactly the opposite direction. In this manner, time reversal symmetry is preserved, which means that actually the Chern number is guaranteed to be 0. So there's a new kind of topological invariant called the Z2 topological invariant. Z2 means that it's binary, so it can be either 0 or 1, which means that either you have this integer, or say odd number pairing of this sort of spin polarized helical modes, or if it's the number is 0, then you just have a normal kind of insulator. If I go through the same thought experiment of what kind of conductance would I get if I just put my DMM on this schematic object, we're actually going to get h over 2e squared. This comes from the fact that, say, we're biasing from here. We have one mode on each side that can carry the electrical current and gives us this factor of 2. So this is where it began, and it was quickly expanded to 3-dimensional systems. So you can have a 2-dimensional helical electron gas on the surface of a 3-dimensional insulator. And there are many, many other symmetry classes that are beyond what we need to know here. But we would like to know, why do we care about these so-called topological systems? Well, for quite a long time, we've already known that the quantum Hall effect has been used for precision metrology by having such a well-quantized Hall resistance or in 2-terminal perhaps two-terminal conductance, you can measure voltages very, very precisely, for example. There are new types of phase transitions occur, such as topological phase transitions. And one of the efforts of the Sequem Center is to try and imagine how we can make some sort of topological field effect, where instead of tuning the density of a system, maybe you can change the topological invariant of a system and use that as some kind of useful switch. And then finally, there's the notion of topological quantum computation, which comes from engineering interesting quasi-particles that are neither fermions nor bosons. And there are many schemes that don't necessarily involve true topological insulators to engineer such a state. And you're trying to engineer a sort of topological superconductor. This includes situations with semiconductor nanowires or quantum spin Hall insulators. And the key point here is that if you have a helical mode, and then you have it proximatized to a superconductor at some part, and then a magnetic insulator, this is M is a magnetic, not metal, on another part, then at this boundary, you'll get a Majorana zero mode. And this is the object that is being sought after in a large variety of experimental systems in order to hopefully realize a topological quantum computer. Now, with that, I'm not going to go into great depth about this. All of these sorts of material proposals to try and get even this fundamental particle have at least one thing in common that I'd like to point out, which is that all of these require some sort of materials hetero interface. Okay? So we have, say, the nanowire you have to get rid of this oxide layer or avoid it. That would occur on the semiconductor nanowire, and then deposit a superconductor. Ideally, your superconductor will be epitaxial, so you can have as clean of an interface as you can. This has been pretty much achieved, and there's a lot of excellent results happening there. And there are many other materials interface platforms that are being used to try and access this sort of physics. Okay, but the reason that you need these interfaces is that robust superconductivity typically requires extremely high density systems, really good metals, and they're typically conventional. And then you need the helical mode. So these are low density. In case of a topological insulator, it is literally an insulator, so zero density in the interior of the system, and require strong spin orbit coupling, and anyway are comparatively rare. So with that done, my graduate work has either been directly involved in or touched on a lot of these sorts of directions, but today I'll be focusing entirely on tungsten ditelluride, and in particular how it relates to 2D topological insulating states. So let's briefly review the experimental status of 2D topological insulators. So there are two dominant materials platforms that generate the topological insulating state, which is a mercury telluride quantum well and an indium arsenide gallium antimonide bilayer quantum well. These are buried semiconductor heterostructures, and they both have very nice qualities that are indicative of a quantum spin Hall state. But they have a couple of limitations. One is that the bulk band gaps are relatively small. That means the interior of the 2DEG has a small band gap, and this has resulted in relatively low temperature operation to access the physics of the edge modes. The semiconductor heterostructures are buried by a capping layer, and this makes it actually difficult to interface the 2DEG with, say, some interesting other system like a superconductor. And then finally, the role of time reversal symmetry is not entirely clear. There's been some questions brought up, but this is more of a side point that I refer you to these references here. In light of this, there's been a number of many proposals in the last, since the inception of topological insulators, proposing different kinds of monolayer crystal platforms that should also exhibit this physics. And the reason is that in these systems, it has been predicted that they will have large band gaps, hopefully allowing for higher temperature operation. The exposed surface hopefully means that you have an easier time making interfaces with other materials. And then finally, in cases where they would exfoliate, you allow for the full toolkit of Van der Waals heterostructures that I described before. And tungsten ditelluride is just one of these predictions. This was predicted by Liang Fu and his colleagues a few years ago. And what they realized is that, unlike the traditional semiconducting transition metal dichalcogenides like moly disulfide that have this type of crystal structure, if you can actually distort into this 1T prime structure, you can actually be a topological insulator or perhaps a semi-metal. And tungsten ditelluride happens to be singularly stable in a phase very, very close to this 1T prime structure called the TD structure. And this is an actual crystal that we've received from our collaborators, Bob Kava, where you can see, this is sort of a side view, and you can see very clearly that it has a layered structure and it's already sort of peeling away from itself like the pages of a book. And this is very nice because, you see you have this nice big crystal, the scale bar is a millimeter here, that you can work with for exfoliation, and it's very likely that it will exfoliate, and indeed it does. Another nice aspect about the bulk crystals is that it's a high mobility semi-metal. And you know, the semi-metal part maybe is tangential, but the fact that it's high mobility is important. Even in the first bulk crystals grown in the Kava lab, the Magnetoresistance, this is the Magnetoresistance in percent on the log-log plot, as a function of magnetic field is in excess of 10 to the 7 percent, so a relative factor of 10 to the 5 at these high magnetic fields. This is pretty exceptional and is indicative of not only high mobility, but almost exact compensation of electrons and holes in the system. This is a cartoon. It's not an actual band structure, but just a schematic to emphasize that you need pretty close compensation to get this sort of thing. This tells you that there's no sort of intrinsic doping, and the mobility is rather high. And so that's really wonderful. We have a beautiful exfoliable crystal, and we apparently have a high-quality crystal to start with as well. Now, let's exfoliate it and see what happens. And unfortunately, as it turns out, like I implied at the beginning, these systems oxidize on their surfaces. And when you have only a 2D crystal, you literally have a surface as what you're working with. And if you do normal fabrication processes, you get something like this, which I'll describe now. Here you have the conductance per layer as a function of temperature. And in the bulk compound, you see that it's nice and metallic. The conductivity rises by a few orders of magnitude as you lower your temperature from room temperature down to about 4 Kelvin. As you measure thinner and thinner samples that have undergone fabrication, you see that this temperature dependence gets weaker and weaker. And then as you go to the thin limit, it ultimately becomes insulating. Now, you might say, OK, well, what didn't you want an insulator in the first place? And the answer is yes, but not like this. These states are not topologically insulating. This is just due to chemical reactivity and oxidation. Okay, so you can see this a little bit more visibly if you take an as-exfoliated crystal and take an optical microscopy image. Here is the background in pink, and then you have this monolayer region, this bilayer region. You wait a few days, and you see that, OK, this has almost completely disappeared. This has gotten fainter, and this has gotten fainter. So you can see that actually this is changing over time, and that's not what you want. So our goals when we started this project is that we wanted to be able to demonstrate non-degraded behavior in fully fabricated devices, and then eventually test for quantum spin Hall behavior in the monolayer. And in light of the proposals for topological devices, we wanted to add superconductivity. But for the first point, tri-layers and thicker samples were expected already to be a semi-metal like the bulk. All theoretical calculations agreed on this. And so because we have a nice reference system like as in the bulk, we can use the tri-layers or similar thicknesses as our sort of canary in the coal mine to see if our new fabrication techniques will work. And what we set out to do, and you know, we're not necessarily the first ones to have done this, but we built our own glove box system where we have an argon environment here that's protected from the atmosphere outside, where levels of oxygen and water are highly suppressed. And inside we can have a microscope and remotely operated transfer setup so that we don't have to have our hands in the gloves all the time, and allow us to do some protection schemes to do fabrication on these systems. So the scheme is something like this. So we have the argon atmosphere inside this dashed line. Boron nitride we can exfoliate and characterize outside of the glove box just because it's air stable. And then the tungsten telluride we exfoliate and inspect in the box before doing any fabrication. Here we have our glass line and our sticky polymer, and we bring our boron nitride inside and pick that up first. This very clean bottom surface of the boron nitride is then used to pick up and protect the top surface of the tungsten telluride. And then finally, for example, we can come down and encapsulate it on both sides with boron nitride like that. We can remove the stacking procedure materials, and then, if we want to, take it outside of the box for further processing. So a real device will look something like this. This is a top-down optical microscopy image. This is in teal on the outside. This is where all the boron nitride was that encapsulates on top and bottom. We have etched here, you can see in the dark regions, so that in the center we have a Hall bar-like structure. And in purple is designating roughly the borders of the original tungsten telluride flake. So you can see that everywhere in the Hall bar we will have tungsten telluride for our 4-probe measurements. Here is a cross-sectional schematic. What I didn't show in the previous stacking procedure is that we have graphite, few-layer graphite on both sides except for the central channel that is used as an electrical conduit that maintains a van der Waals seal in order to be able to continue measuring the device without having it degrade to air. So let's see if it works. The first point is let me first review what happens with bulk samples and exposed samples. Here's a sample we measured in our own lab in a semi-log scale. The resistance is a function of temperature, and we see this nice metallic temperature dependence, where the resistance drops by a couple orders of magnitude. If we take a several layer thick sample that's exposed to air and lower the temperature where it rises up, we see it rises up, and that's indicative of degraded behavior. And if we take a 3-layer sample that's been fabricated in the scheme I just described, we see that the resistance does drop nicely with temperature by about an order of magnitude, indicating a nice metallic state. So that's a good start. And the next thing we want to know is it a metal or semi-metal? For example, did the fabrication procedure dope the system, or did something else happen, or does it look like the bulk samples like we would like? And one of the ways we can do this is with magnetoresistance. So just to start, we see very immediately this is the relative change in resistance as a function of magnetic field, and we see this nice nonlinear increase that doesn't quite show any signs of saturation up to our largest magnetic fields that we can apply. And this voltage represents our gate voltage on our field effect device. And the main point of having this is that unlike bulk samples, in 2D you can use the field effect to change the density of the sample and see how physics evolves as you do that. And indeed, as we dope the sample by adding electrons and subtracting holes with positive gate voltage, we see that the same nonlinear increase at low magnetic fields, saturating to a constant at large field. And then at the highest gate voltage we can apply, we see no magnetoresistance whatsoever. So now with this data in mind, let's take a brief review about what happens. Why do you have magnetoresistance in a semi-metal and not for a simple metal? So for a single carrier system, so imagine you just have a conduction band and only one type of carrier of electrons. You apply your current along the channel and you get your electric field lines. And then you apply a magnetic field. And this magnetic field gives you a Lorentz force, which causes electrons to pile up at the top and bottom of the channel, and gives you a Hall electric field that at very high magnetic fields can actually dominate the electric field profile of your sample. In the case of a semi-metal, at high magnetic fields, you get both electrons and holes piling up on opposite ends, and if at exact compensation, these cancel out, and you can imagine that the electric field profile is actually the same as it was at zero magnetic field. However, no matter what exactly is going on regarding these electric fields, your local equations of motion don't change, and what we have added in a magnetic field, we have this general prefactor that reduces your drift velocity as a quadratic function of magnetic field, but you also have this E cross B drift. So this E cross B drift, I think many of us have solved in our electrostatics and electrodynamics classes, and the main consequence of this E cross B term is that in a single carrier model, you have now your electric field pointing up and your magnetic field pointing out of the plane, and you actually get an E cross B boost along your channel direction, and you actually don't get a magnetoresistance for a simple metal. Whereas for a semi-metal, your electric field profile is still along the channel with an out-of-plane magnetic field, and you actually have a transverse velocity. And so as a result of this, you can take the component that's along your channel of the local current density of each carrier type, and you get a quadratic suppression that you don't have in the single carrier model. So as a recap, for the simple metal, you have a constant magnetoresistance. Imagining here you have, say, a single Fermi surface of electrons and no change in resistivity as a function of magnetic field. For a compensated semi-metal, you have a quadratic increase of the resistance that, according to the semi-classical equations of motion, does not actually saturate ever. So something else will have to kick in at higher magnetic fields to eventually get it to stop. And then finally, you have an uncompensated semi-metal, where if you have, say, both electrons and holes present, but more of one than the other, then you have at low fields a quadratic magnetoresistance saturating to a constant at high field. And this is indeed quite reminiscent of what we have in our devices. Okay? So we also have a Hall bar geometry, so we can measure the Hall effect and compare, and we see indeed that at these large gate voltages, the holes are completely depleted out of the system, and we have an electron-only device. You may also notice that we have these nice little wiggles here. These are actually quantum oscillations that are indicative of high mobility in our samples due to Landau quantization. So this is the change in resistance as a function of inverse magnetic field for this electron-only regime at high gate voltage. And we see, if you're used to looking at these things, you can tell that there's two frequencies here. By taking the Fourier transform, we can see that quite explicitly. And we can then look at how all these evolve as a function of gate voltage, and we can get this map of these oscillations as a function of gate voltage and magnetic field, and do the same kind of Fourier analysis and find that, okay, there is this fan, this weaker fan that seems to extrapolate to depletion at around 100 volts, and then we actually have two electron pockets present at high density, which is likely due to a spin-orbit splitting inside the system. Okay? So, so all things considered, I think we've managed to develop an experimental capability in the lab to make fully fabricated tungsten telluride devices that display non-degraded behaviors. The next thing to do is to test for quantum spin Hall behavior in the monolayer. So with that goal in mind, one of the first things to check is whether the system is actually a topological insulator. Does it have a full transport band gap? What I didn't mention before is that the initial calculations showed that, okay, here's your valence band. This is energy and momentum. Here's your conduction band. They're actually not quite touching here. They're actually overlapping in different parts of momentum space. This would mean that you actually have a semi-metallic state, just like what I described to you in the tri-layer and for the 3D samples. But then there was some follow-up work that showed, oh, if you do your ab initio calculations another way, you get a huge band gap for the monolayer, and maybe a small one for the bilayer, and then return to a semi-metallic state at thicker and thicker systems. So there was some disagreement amongst the theorists, and experimentalists, we go and actually do measurements, and there's been a lot of great work for example, from the Washington group on transport devices, which Sanfeng was also involved in before he came to MIT, and then spectroscopy, both with photoemission and scanning tunneling microscopy, to show that indeed the system is a true insulator. In the transport devices, you see that they've done some clever device geometry techniques to show that here in blue, they're probing largely the bulk conductivity, and they see that for a range of gate voltages near charge neutrality, the bulk conductivity is actually 0. And if you allow for looking at currents flowing along the edge, you see some edge conduction that is there in the system. So this was very promising results towards determining the system as being a possible topological insulator. In spectroscopy, both scanning tunneling spectroscopy and angle-resolved photoemission have found that there is a band gap of around 40 to 50 millielectron volts in the system, and you can see these beautiful band structures that give us information of actually maybe how we should do the calculations to understand the band structure of the system. So the bulk has been confirmed to be insulating, but what is missing is to see that the edge states that appear to be present can actually be made to approach the quantum of resistance per edge. And then we want to test the requirements of symmetry, time reversal symmetry in particular, once we have this quantized edge conductance. And so the strategy that was employed in our group is to use a device structure like this. So I'm going to go slowly. There's a lot of things happening here. At the bottom in orange, we have these finger gates that are long and narrow. And each of them has a different length in this dimension that we're going to call the channel length. On top of this, we place our boron nitride dielectric that we then, on either side of the gates, on top of this dielectric, we place these electrodes. Everything is designed so that the height of the electrodes matches the height of the boron nitride in the center, so we can have a nice flat device structure. We can then place a piece of tungsten ditelluride spanning all of the contacts, and in particular, by touching here, we can make electrical contact to flow current through the device. We have a top layer of boron nitride covering the tungsten telluride everywhere, and additionally, a top layer of graphite that also covers the tungsten telluride everywhere. The key idea here is, one, to dope the tungsten telluride at the contacts to achieve an ohmic contact here, and then separately, the philosophy is that the best way to contact the edge mode is with the two-dimensional conduction band states of the tungsten telluride itself. So that goes as follows. We first energize the top graphite gate to have doped 2D electrons everywhere in the tungsten telluride, and we measure some resistance. And then we take this local gate that has a fixed dimension and start to deplete that area of the sample back into the band gap of the sample, of the material. And as we do so, the resistance starts to rise. If this is a simple insulator, then the resistance should go up ad infinitum. If it's a Dirac system like graphene, it should come right back down. But instead, what we see is an approximate plateau that, where I've drawn these lines, is a difference of resistance, this step height, which is approximately half of the quantum of resistance, which is strongly indicative of having a single helical edge mode at each edge of the sample. And here we have two. So let's zoom in on that. This is the change in resistance as a function of this local gate voltage for 3 different local gates of different dimensions on 2 different devices. So again, we start out here where we have a fully doped system, and as we deplete, we get this approximate plateau at slightly higher than half the quantum of resistance. And the way we understand the factor of 2 here is, again, the fact that we have 2 edge modes, and when you apply a bias from your source to your drain, you have a single mode on each side so a total of 2, giving us h/2e squared. Now, it's always possible that these modes are not actually ballistic or close to ballistic, but instead some trivial diffusive edge of some given length that happens to give you this value of resistance. And so what's advantageous about the design I showed you with all of these different gates is that a single device can give you multiple different channel lengths. What we show here is this is the edge resistance as a function of length on log-log form. Each color represents a different device, and I'll draw your attention specifically to the green and black data points, which represent a different gate that we use on that device. And at long length scales, we would see that the edge resistance is generally increasing, but it does not follow Ohm's law and instead starts to saturate, in both cases, towards this value of h/2e squared that you would expect for short length scales on such devices. Okay, so this is all well and good, and now the next thing is to see what happens when you break the symmetry that protects the topological state. If we go back to this cartoon image of these counterpropagating modes at zero magnetic field, we can zoom in and imagine a band structure for these modes. And if you have a clean edge, you can say that you have a Kramer's point here. So you have this mode with one group velocity and a particular spin in purple, and the other one in red. And at this point, these two states are degenerate. In particular, you have a spin degeneracy there. And when you have a spin degeneracy, a magnetic field can break that via the Zeeman effect. And in doing so, you can generate a band gap in the edge mode. So here, schematically, these edge modes have become less conducting. And in particular, if your chemical potential is inside the gap, it should behave like a simple insulator. You've broken the topological protection of the system. So, OK. This plateau resistance that I've shown you, we've inverted to conductance here. And so we have this curve at zero magnetic field as a function of the local gate voltage. You can think of this as a chemical potential. And as we turn on a magnetic field, initially, the conductance generally drops. All right? So that's the first stage of what happens, what we observe as we turn on a magnetic field. And then as we turn it on a bit more, you can see that, I'm going to go back and forth a few times, here on the left and on the far right, not much happens in this second stage, except right here where we see another full order of magnitude reduction of the conductivity as a function of field. And we can keep going, and you see here again that it is dropping precipitously. Note the log scale, by the way, on the y-axis. So this would seem, in spirit, the right idea, that you have perhaps right here your chemical potential is at the Kramer's point, and then you can open a gap if your chemical potential is there. And indeed, we can take a line cut at a particular gate voltage and see that the conductance does indeed drop exponentially in the semi-log plot as a function of magnetic field. And moreover, as we turn on the temperature, we go hotter, this exponential reduction is reduced, as we expect for thermal activation over a semiconducting gap. So the typical thing to do here is to say, OK, we'll take an Arrhenius plot of the conductance. So this is the log of conductance versus 1/T. And then if we do it at every magnetic field, that would be a bit tedious. But instead, we say, OK, let's assume that our gap is linear in magnetic field and just put it here in the prefactor of the 1/T of the Arrhenius plot. And we find that all of the data points collapse onto the same trend. And that tells us that, indeed, we have exponential suppression with thermal activation where your band gap is linear in your magnetic field. And by doing this fit, we can extract an effective G factor for this orientation of magnetic field, which is about 5. So if we believe that this point in gate voltage is at the Kramer's point, and we have put our chemical potential inside this band gap induced by a magnetic field, then on either side, we should expect that we have some sort of 1D mode that with a finite chemical potential. Presumably, it should conduct a bit, and yes, it does. And we can actually try to understand why is there some reduction of the conductance, but not complete suppression. And just to give you an idea, at a few selected gate voltages, here's the conductance as a function of magnetic field. And you see it drops initially and then starts to saturate at high magnetic fields. Here in red is the data at this gate voltage where you see it's really trending towards 0. And what we can understand, one thing that we can draw from is some theory work in the literature, which has shown that if you have small puddles due to disorder in your device and a finite magnetic field, then you enable elastic backscattering. And you can do that. What you can understand is that when say the spin-up forward-moving electron hops into the puddle, it can then randomize its spin, and then it will have a 50% probability of jumping in a forward direction or a backward direction, and therefore backscattering has been enabled. With a few of these dots, causing backscattering along the edge on either side, we can get this small reduction of conductivity that's not exponential in the magnetic field. And indeed, they do predict exactly this sort of shape where it drops very quickly initially and then saturates. So there's in concert with all of the other work that's been done on tungsten telluride in the monolayer, we do believe that we have pretty good evidence that the system is a 2D topological insulator. And there's plenty of other work to do, particularly spin polarized measurements and non-local measurements. But this is a nice place to start. And one other bonus, a cherry on top, is that we believe that we've seen that there's a nice signature of the large band gap in the interior. Here's the channel conductance again at close to 2e square over h as a function of temperature. And we find that it is roughly constant up to about 100 Kelvin and then starts to go up. In this region, we believe that the 2D carriers here have been thermally activated and are starting to contribute to the channel conductance. But everywhere below 100 Kelvin, it appears that the system is dominated by the edge modes, which holds promise for topological devices that work at above 4 Kelvin. Okay. So finally, we wanted to add superconductivity and try and do perhaps a proximity effect study on these edge modes. But nature threw us a bone that required us to do a bit of different investigation. Imagine that we have the same device, and in fact, it was the same device as that I've been showing you over the past 10 minutes or so, but now completely doped with no depleted region in the sample. And we simply took this thing to lower temperature, and we found that the resistance drops starting around 1 Kelvin and going down by about a factor of 6 on this device. You can see here that it doesn't get quite to zero resistance. It may be due to a finite temperature. It could also be due to the fact that it's likely due to the fact, that this device geometry will always have a small sort of contact resistance that we aimed to get rid of. So we then followed up with a new device geometry that allows for a full 4-terminal structure, which allows in particular that between every set of contacts, you will have tungsten ditelluride that is sandwiched on both sides and protected from oxidation. And this will would hopefully allow us to measure zero resistance and prove that the system is indeed superconducting. And it does work. So here's the resistance as a function of temperature for a selected gate voltage. And it drops, again, starting from around 1 Kelvin and reaches 0 at around a little bit above 300 millikelvin in this case. And a little bit later, I'll be designating TC just for convenience at about the halfway point compared to the normal state resistance. We can then do this sort of basic characterization. So we have the 4-terminal voltage as a function of DC current bias. And we see, again, no voltage drop at low temperatures up to some value. And we see a very sharp onset voltage rise at a particular current that we'll call the critical current. As we increase the temperature, we see a smooth transition from this highly nonlinear behavior to typical ohmic behavior of a standard metal. The fact that a 2D system can actually undergo a full zero resistance superconducting state was another major component of the 2016 Nobel Prize. This is the quote from the announcement. So this is also, when it comes to topology, we have sort of two aspects of this prize here today, here in this material. We can replot the same data. Instead of a VI curve, we can do the differential resistance. This critical current now appears as a sharp peak. And as we increase the magnetic field, we see that we remove the nonlinearity and again return to a simple metallic state, again showing that, as expected, magnetic fields kill the superconducting state. Now, what I described a minute ago was that the system, we just have to dope the system to reach here. And I've already shown you that we can also dope into the insulating, the topological insulator phase. So I can show you, for example, the temperature versus gate voltage diagram of the relative change of resistance compared to high temperature. And we see that, say, at high doping, we undergo the same superconducting transition where we reach zero resistance, again, at around 300 millikelvin up at high density. This line indicates the 50%, the critical temperature as defined by the 50% value relative to the normal state. As we deplete, the critical temperature gets lowered, and eventually we get to a point where there doesn't seem to be much temperature dependence at all. And then at yet lower density, we go from white to red, which indicates an insulating temperature dependence, indicative of the topological insulator phase. So it turns out that this superconducting state, this density is around 5 × 10⁻¹² per centimeter squared. It's one of the lowest density 2D superconductors. It appears to be the lowest density superconductor as measured by induced density that we're aware of. And this allows us to draw an initial preliminary schematic phase diagram with temperature and density here. We know about the quantum spin Hall phase that can exist up to, dominate the transport of the system up to 100 Kelvin, and the superconducting state that exists up to about 1 Kelvin for all high densities, and this metallic phase in between. And the fact that all of this is accessible within a very low carrier density range allows us to envision new kinds of devices that will, topological devices within a single homogeneous material without any new materials interfaces. So for example, the same device structure that I showed earlier in the talk, where we have the doped tungsten telluride on either side of the undoped region with the helical edge modes, at lower temperature, we will have superconductivity on either side and hopefully proximatize these edge modes. If this is short enough, we'll hopefully get a Josephson effect.
From the phase diagram that you showed, it seems like you should go like superconductor, metallic region, spin all of it.
Yeah, so we can't necessarily confirm in this narrow region here whether it's a sharp transition from superconductor to insulator or if there's something intermediate there. I mean, we're not necessarily at low enough temperature. And we have this complication. You see this little shoulder here that may be due to an inhomogeneity in the sample that may complicate our analysis. So we're not presuming anything necessarily to happen at this critical density. But I'll note, for example, that we have another device where the critical density appears to be slightly lower. Okay, so this may not be a universal value. We may not have found the universal value for this density yet. So we're trying not to be too presumptuous about what happens here. So we hope to have a Josephson junction with these helical edge modes defined in the same material simply by gate voltages. And beyond this, we already know that magnetic fields will gap the edge modes. And 2D superconductors with strong spin-orbit coupling are known to be relatively insensitive to in-plane magnetic fields. And what we can hope to do is by using in-plane magnetic field at very low temperatures to induce a gap and an insulating phase in the helical mode here, but also preserve the superconducting state on either side and maybe realize Majorana bound states at these corners, which can be potentially inspected via spectroscopy, some sort of spectroscopic tool. So I will leave you with that. If I'm happy to answer any questions, and I have some slides, but I'd like to put up the team and our collaborators again and open up to questions.
Yeah, so I was just curious, in other TMDs, like MOS2, they have to use ionic gates to gate it up to 10 to the 14 or something to see superconductivity. Why do you think you can see it? Is there any like physical mechanism for it? Or?
There must be, but we don't know what it is at this time. That would be a very interesting direction for sure. But yeah, it's a bit of a mystery why there's superconductivity at such low apparent induced densities in the system.
Just coming back to the phase diagram, so the experiment that you showed, like of quantized edges. So this was like the contact were in the metal region and the.
So this, right? You're wondering about where the contact is.
So you showed like this phase diagram of superconductor of metal.
For the superconducting device. This guy? Or do you want to look at the phase diagram? You want the phase diagram, okay, here?
So the experiment that you showed of 2 over H.
Yeah.
So the contact were like on the metal region, and the bulk was in the quantum spin Hall insulator. That's the. And if you would lower the temperature, the contact would be superconductor. That's the idea.
Yeah. So recall that this is exactly the geometry of that first experiment. Mm-hmm. And yeah, so we dope everywhere in the sample into the conduction band of the same material, and one local region back undoped into the insulating potentials. And this apparently makes pretty good contact, and in this case, metallic contact for now.
from the
And the
build
idea
state to the
that if you cool it more,
Yeah,
so
you
just
could-
the contact will become superconducting.
That's right. That's the concept, and hopefully the transparency is as good as it seems in the metallic phase to give us a nice proximity effect.
So does the superconductivity remain to the highest densities that you have? Or
Yeah, as far as we were able to push it. Yeah, we didn't see a peak on the dome per se.
Yes.
Yeah, no, we're not aware of how high density this can go. That's a good
Just
question.
another order of magnitude density and we get to room temperature.
Yeah.
You extrapolate.
Very, very slowly. Yeah.
Nine question. How do you know the density of the electron of the superconductor?
Yeah, so we have both Hall effect measurements and CV measures, so capacitance and voltage. So that's the first order thing. How much density have we induced
So
in the system?
Is it down in superconducting state? What's the
Oh no, at slightly higher temperature. We go above the critical temperature of the superconductor to do all.
It
To
should
do.
be same. I mean,
It's in the normal state.
It's in the normal state that we measure.
Yeah. I mean, but so how can we think the density of state is same with normal state and superconducting state?
The density of states? The density of electrons? Yeah, that's a good question. I mean, even to measure a Hall effect in the superconducting state, you have to first kill superconductivity with magnetic field and then measure things. I'm not sure. Maybe if you do a quantum capacitance measurement, you could imagine doing something like this. But we haven't done such a thing.
But the way of thinking, the way to think about it is, you have this system, you put a density of 5, 10 to the 12 in the normal state, and you cool down, and it becomes a superconductor.
Yeah.
Now, the density may or may not change, but you're making the same comparison with any other material. The density is always determined in the normal state, and then you cool down.
Yeah.
So you're quoting what is the density in the normal state, for which, when you cool down, the system becomes superconducting. Are there any other questions?
All right. Well, I'm happy to speak privately with anyone afterwards. If there's any.
Okay, if not, let's thank Valla again.